Solving exponential equations. So when you're looking for the exponent, you can use a log function because logs are the inverse of exponential functions. For most exponential equations, you can use any log function that you wish. So I'll use the common log. From the rule of logs, you can bring the exponent out front. And the log of 3 is just a number, so you can divide both sides by the log of 3. Log of 3 divided by the log of 3 is equal to 1. And we get 1.46 if we round off to the hundredths place. You can use the rule of logs and take the log of both sides right away. I prefer to simplify each side as much as possible before taking the log. So I'm going to divide both sides by 7. Seven over 7 equals 1. And you can just leave that as a fraction to prevent rounding errors. Then take the log of both sides. You can use the common log or the natural log. And using the rule of logs, the x comes out front. And we can divide both sides by the log of 2. It's worthwhile practicing typing these in on the calculator. So that's my common log. Notice that it types in the first parentheses. Be sure you type in the second parentheses yourself. It types the first parentheses. You type the second one. I'm going to round off to the hundredths place, so I'll use the approximately equal sign. If you're solving exponential equations, which include the base e, then there is an advantage of using the natural log. So we take the natural log of both sides. The rule of logs allows us to bring the exponent out front. And then we can simplify using the fact that the natural log of E is equal to 1. So x times 1 is the natural log of 5. I like to get in the habit of closing the parentheses. If I round off to the hundredths place, I get 1.61. The number of spiders was initially 150, so that means at time 0, and it is increasing by 7% per month. So we can use the exponential equation of this form. A is my initial value, which is 150. The 1 represents 100% of the initial value, and R is the rate of change. And because it's increasing, that's a positive 7%, but we write it in as a decimal. So the base of my exponential function is 1.07 to the x. And then I'll just make a mental note that that's per month. How long will it take the population to double? So I'm looking for the time when the population is double the initial amount. So 2 times 150 is 300. So that's my y value, or f of x. I like to simplify as much as possible before taking the log of both sides. So I'm going to divide both sides by 150. $150 divided by 150 is equal to 1. 300 divided by 150 is 2. And now I can take the log of both sides using any form of log that you wish. You'll get the same answer using the common log or the natural log. So the rule of logs lets me bring the exponent to the front. And I'll divide both sides by the log of 1.07. So my solution is the log of 2 divided by the log of 1.07. That's the log of 2. Close the parentheses. Divided by the log 1.07. Close parentheses. I'm going to round it off to the tenths place. I'm going to use approximately equal since I rounded. And then because this was per month, that is the number of months. The number of weeds in my backyard is increasing by 5% per week. How long will it take the initial number to triple? And you'll notice no initial number is given, so we'll just use a constant. Use A to represent the initial number. How long will it take the initial number to triple? We're looking for the time when the initial number is triple. And it turns out with an exponential function, the tripling time, doubling time, half-life, any of those, does not depend on the initial amount. It only depends on the rate of change. So my rate of change is increasing, so it's positive. We write it in the function as a decimal. So my function is A times 1.05 to the x. I want to find the time required for the initial amount to triple, so I just put 3a for my y value. And then I divide both sides by a. A over a equals 1. 3a over a equals 3. And now that I've simplified it as much as possible, I'm going to take the log of both sides. Bring the x out front. And divide both sides by the log of 1.05. So my tripling time is the log of 3 divided by the log of 1.05. So log of 3, close parentheses, divided by the log 1.05, close parentheses. I'm going to round it off at the tenths place. And my x was the number of weeks. If we had used the natural log, my final equation would be natural log of 3 divided by the natural log of 1.05. And we'll just calculate that to show ourselves that we get the same answer. The radioactive substance polonium decays at the continuous rate or relative rate of 8% per year. What is the half-life of polonium? Well, the half-life is the amount of time required for the initial amount to decay to 1/2. And again, it doesn't depend on the initial amount. Because the rate is given as a continuous or relative rate, we use this form. My rate is 8%, but because this is decay, this is a decreasing function. So we're going to use negative 8%, but we put it in the formula in the form of a decimal. It's going to be negative 0.08. So my function is the initial amount times e to the minus 0.08x. To find the half-life, I'm going to put this in for the y value. I'm going to divide both sides by a. And then I'm going to take the log of both sides. And because I'm using the base e exponential function, I'm going to take the natural log of both sides. Now all of this is the exponent, so that's what goes out front. And then we can simplify this equation by using the fact that the natural log of e is equal to 1. I divide both sides by negative 0.08. So the natural log of 1/2 divided by negative, we have to use a little negative key here, 0.08 is equal to, I'm going to round it off at the hundredths place. And this was the rate per year. So that's the number of years. So this rate, this amount of time for decay by half, is independent of the amount of the radioactive substance. The population of ladybugs is 100 and is increasing by 12% per year. The population of grasshoppers is 400 and is increasing by 2% per year. When will the populations be equal? The ladybug population can be written as 100 times 1.12 to the x. The grasshopper population is 400, 1.02 to the x. We can find the time that they'll be equal by setting the two functions equal to each other. And you can take the log of both sides at this point But I like to simplify as much as possible before taking the log. So I'm going to divide both sides by 100. And then I want to get all of the x on the same side. So I'll divide both sides by 1.02 to the x. So I get 1.12 to the x divided by 1.02 to the x equals 4. And then we can use the rule of exponents. If a over b to the x equals a to the x over b to the x, well, this looks like a to the x over b to the x. So that's the same thing as 1.12 divided by 1.12 divided by 1.02 to the x. And now I can take the log of both sides of this equation. I bring the x out front. And then divide both sides by the log of 1.12 divided by 1.02. We get the log of 4. Don't forget to close the parentheses. Divided by the log of 1.12 divided by 1.02, close parentheses. And we get, I'm going to round off at the 10th place. And make a note that this was percent per year. So the two populations will be equal in 14.8 years. Find the exponential function of the form f of x equals a b to the x, whose graph is given here. So I have 2 points. I don't have the initial value, so I don't know the a. Let's just plug the 2 points in and see what happens. So 2, 5. 5 is the y value. 2 is the x value. Plug in 9, 12. So I get 12 equals a b to the 9th. And then we can take the ratio of the two equations. 12 over 5 is a b to the 9th divided by a b squared. And a over a is equal to 1. I get 12 over 5. Using the rules of exponents, I get b to the 7. I don't need to use logarithms for this because the exponent is known. I can simply take the 7th root of both sides. And one way you can find this on your calculator is 12 divided by 5. And use your exponent key. 1 divided by 7. And we get that b is equal to 1.1. Let's do it together. Twelve fifths. There's your exponent key. 1 divided by 7. And the calculator stores your last value. So let's leave it in there because rounding errors can really affect your answers in exponential functions. So I found B. I want to find A. So I can use either of these equations. If I divide both sides by b squared, I get A. Go over here. So the calculator saved my last answer. So we can just type it in, 5 divided by second answer squared. I'm going to round it off here. And now that I've done my calculations, I can round off. Let's round off to the hundredths place. And then if we look at the graph, well, my initial value is around 4. That looks correct because that's less than 5. And then my function is increasing because the base is bigger than 1. And that looks right with my function. And another way to check it is to take this equation, plug in 2, see if you get 5. Now, because we rounded, it'll be close to 5. Plug in 9, see if you get 12. And again, because we rounded, it'll be close to 12.